Okay, good afternoon, everybody. I think I will slowly start my tutorial. I am Stefano Balbi. I am based at the Basque Center for Climate Change, and I'm an ICER Basque Research Fellow. The Basque Center for Climate Change is participating in the ARIES project, which, as you have understood from the presentations this morning, is an Interreg project on the Atlantic area. And we are in charge of integrating the modeling approaches used in the project in a way that basically everything that is produced by the partners can be used in an integrated modeling fashion. Sorry, I was reading the chat because they were telling me that my face didn't show, but now is I think showing properly. There is a little bit of delay between what I'm saying and what you see in the live channel in YouTube, so there might be 20 seconds lag. So I'm here to talk about k.LAB, a software that we develop in BC3. And I need to start by explaining ARIES first. So ARIES, I cannot even. Okay, ARIES stands for Artificial Intelligence for Ecosystem Services. It's a project that was born in 2007 in the United States with a fellowship from the National Scientific Foundation. And from 2012, this project is based in the Basque Country at the Basque Center for Climate Change. Also, in the last years, we had a lot of support from the Basque government and the ICER Basque Science Foundation. And this is where we are now. So artificial intelligence for ecosystem services. This project is about ecosystem services originally. Why? Because ecosystem services are one of the most complex issues to be modeled, because they are about the relationship between nature and human societies. So, for example, you have this schematic representation in this slide where you have nature on the left side and societies on the right side. And ecosystem services are the benefits that are flowing from nature to the society. And as you can imagine, we are enjoying so many benefits from nature, and all kinds of complexities can be considered in modeling ecosystem services. And so it's the typical case where basically we need a lot of knowledge to explain a very complex phenomenon. And this knowledge is very often is compartmentalized and needs to be integrated. So that's why the project was born with this idea of integration and basically using granular and modular modeling components to establish ecosystem services modeling workflow. And these are the words of the principal investigator, Ferdinando Villa. So the paradigm behind ARIES is to use technology to build integration and to break up granular customizable components to represent ecosystem services as they are. So how do we do this? We do this with one branch of of artificial intelligence that is not very much recognized at the moment. So most of us understand artificial intelligence as machine learning, which is basically the way of uncovering pattern in data, while machine reasoning is a completely different branch that uses semantics, so logical declaration and axioms called ontologies, which define concepts and the relationship between them, and then reasoning to link data and model using logical inference to automate their assembly into useful structure for computation. Basically, with semantics and machine reasoning, we are telling machines how to compose models from data and modeling components that are in need of integration. So ARIES is a project on ecosystem services, but in developing ARIES, we have in fact developed a technology for the integration of data and models. So what I'm going to explain today is the k.LAB software. It's a software stack and is, let's say, comprised of many features that I'm going to try to explain as much as possible. And the final aim of this technology is to completely change the way we do modeling. Instead of starting from scratch from our own desktop, to basically use a network of knowledge that is already available and which we can reuse. So the software stack, as I was saying, is quite, let's say, includes a lot of components. The most important one that I want to explain today is the engine. So the engine is the entry door to this networked software, and allows you to enter the network of knowledge of k.LAB. You have received the instruction to start this software in two possible ways. One is with a downloadable software, and one with a direct link in a web browser. So I will try to explain both today. With the engine, you connect to a node that basically, well, first of all, you need to authenticate and create your own user profile. And then when you are in the network, you are basically using many nodes of the network that can contain data and models. And then we have a user interface. So this is the user part. The part that you can actually see is the modeler. This is the part that I'm going to explain at the end of this tutorial. And the part where we will spend a little bit more time is the explorer. That is the user interface for people that want to use the modeling components without actually creating new models. So the type of use that the software allows is simple observation workflow. And basically, this enables you to set a context of analysis and to type a query in a search bar. And this query is completely conceptual. So it's not querying specific data or models, but the machine, through machine reasoning, is able to link all the data and models needed to respond to that query. And for example, there you have an example of how the semantics is written in our semantic language. So you have, for example, the occurrence of pollinator is the presence of pollinators, and this is a required piece of knowledge to respond to the query on pollination. And this query is passed in the semantic network, and the machine is able to construct the computational workflow needed to respond to the question, and then produces the modeling output, which are both maps, but also written reports, so explained in a narrative way, and also the computational workflow itself, fully documented in a data flow like this one. We are going to see this in the tutorial. Because we recognize that this technology that we have developed is completely generalizable, so it's not only for ecosystem services, we have created a partnership for integrated modeling. This is the address. And basically, this is our institution for, let's say, guiding our collaborations with other institutions. Because we want to share this knowledge, we want to share this technology, and everything that I'm explaining today is open source and open access. And we want to keep it that way as much as possible. So, as I was saying in the beginning, ARIES stands for Artificial Intelligence for Ecosystem Services. Used to mean ecosystem services. Now we are rebranding ourselves because we have understood that everything that we are doing is much more than ecosystem services. So we are also doing renewable energy, marine spatial planning, natural capital accounting, freshwater ecosystems, and biodiversity. So the new acronym is Artificial Intelligence for Environment and Sustainability. These are our channels. So please contact us if you are interested in what you are going to see in the next hour and a half. You can find us on all the main social networks. If you have problems with the software, please write to support@integratedmodeling.org. So this is basically the structure of what I'm going to show in the next 2 hours, actually 1 hour and a half. So the introduction was this one. So now I will finish with the slides and I will start showing the software itself. The first part is how to get started with the K-Explorer user interface. The second, after that, I'll do a quick tour of the user interface itself. If you want to go deeper into the subject, I direct you to this link. It's a YouTube tutorial by Ferdinando Villa itself, so the principal investigator of the project. And after that, I will do a quick tour of our ecosystem services related models. Those models are published in a scientific article in Science of Total Environment in 2019. So if you want to have more details about them, please refer to that publication. After that, I will explain a little bit how we are able to further customize the user interface into thematic maps, into thematic apps. And this one in particular is about natural capital accounting. After that, I will give a quick introduction to the modeling user interface. So that requires a little bit more training. So I'm not going to cover a lot in this tutorial. But let's say up until point 4, you can try to repeat everything I'm doing with the online engine. Otherwise, everything else with the downloadable software from point 5 to point 7. Point 7, finally, are the models that we developed for the ARIES project. I will give you an overview of the work behind the models in ARIES Interact project. So this is the end of the presentation. Let me check if I have any message in the chat. I see a little bit messages here. Okay, I will stop checking the chat because it's distracting me a lot. So I will close it here and start with the software itself. So I have a little bit of problem with this part of the screen. Maybe I can go here. So let me start sharing again, please, the screen. Yes. Okay, so now you see, hopefully, the web page itself. It's integratedmodeling.org, get started. So here you can find all the basic information on how to get started with the k.LAB. And here you have the link to the software download. You have it for Windows, for Linux, and for Mac. So you received the instruction about how to do all of this before the meeting. So I hope you did some of the steps you were supposed to do. Otherwise, no problem. Well, supposing you have installed the software, you would have to launch it, and it will start, for example, from here. So the second part is actually to register. This is very important. So you need to go to integratedmodeling.org in the hub, and then register here. In my case, I can log in, for example, and I can click in the profile section and download the certificate. This is very important because the certificate is what allows you to authenticate in the system, so the system knows who you are. And you can download it by clicking it. Well, I can actually, when you click, if you have the end user license agreement, you just click and accept, and it's downloaded. Okay. So you have the certificate, you have your profile, you have the certificate. Now you can actually start the software. This piece of software is called the control center. And the control center, as you see, recognizes me, Stefano Balvi here, and I'm already authenticated. What you need to do in order to be authenticated, you go and you take the certificate where it was downloaded, and you just drag and drop it on this panel here. And then the system will recognize you, so you will have your username here, and then the groups to which you belonged on this side. Now, the second part is, supposedly you are in this situation, you need to start the engine. So as I was saying, the engine is the gate to the network, the semantic web, and you need to click on this in order to start it. So you will see that this terminal window will appear, and then slowly the engine will go online. The engine goes online, and when the engine is online, we are ready to go, and we can use the client, which is a web browser, in order to access the K-Explorer user interface. Give it a little bit of time. So as I wrote in the instructions, you can download the software and do like I'm doing right now. Or for this particular training, we made available this link here, integratedmodeling.org/modeler, which allows you to log in with the same username and password that you have created in the hub. And you can access the online engine. So now I'm still using the software. The engine is online, as you see in the window, and I can use this icon here to start the K-Explorer in my default browser. Now my default browser is, in this case, Mozilla. When it starts, I'm welcomed with this tutorial, which I suggest you to scan when we are done with this tutorial, because I think it's very useful. It contains a lot of information, especially the cheat sheet here. There are many commands that you can try to use and repeat. But for the moment, I will close it. And I am in a situation where basically looks like a normal map with this search bar and an elephant in the search bar. So let me just show you that if I do this in the online engine, so username and password, I log in, and I'm exactly in a similar situation. The tutorial starts, and I'm in a map like this. Perfect. So let's assume that we are, all of us are in this situation with the map and the search bar open in the default browser. Supported browser are Chrome and Mozilla, so mind that, please. This is K.Explorer, how it looks like at the beginning. So it's just a simple, looks like a simple map. You can actually change the background map, and I'm using the minimum. I can use OpenStreetMap. I can use all of these layers. So what do we do now? Well, it's important that we realize this is not a simple map, but this search map actually allows me to introduce my queries. For example, well, this tutorial is would have been based in REN if we were doing the school in presence, but we are not. But anyway, let's try that and type something here. So as I type, the system suggests possible solutions. For example, in this particular case, I'm typing elevation. I can type elev, and this is suggesting only elevation. I just click enter and enter again, and the elephant, the ball of the elephant, as you see, starts spinning and is giving me an answer. And the answer is the elevation map in the region in the map where I am. So you can see that I can click on the map and see the values, but I can also click on the layer itself and see the histogram. I have a lot of information here, the number of cells in the map, and the total area in square kilometers, stuff like that. So this is one possible search to do. And I can search many things like slope and all the geographical variables that you can imagine. But this is much smarter than this. So it's not a way to query data only. It's an actual model. So I can do the same. Instead of searching for elevation, I search for normalized, and I select it, and then elevation. And again, click. So the system now has done something that is similar to before, but it's also very different. Instead of giving me the map of elevation, it has given me the map of normalized elevation. Now, this seems very simple, maybe, but this calculation has been done on the fly, well, after I entered my query. So in the data flow, I can see what this what the system has done. So the elevation information has been fetched online through a web coverage service. And this is a global layer of elevation with a resolution of 90 meters. The original data is 90 meters. And then this information has been normalized. And so the output is this one. I can check again the histogram. Now you see the histogram is different. It goes from 0 to 1. It's completely different than before. And I can download this data if I want. I can browse over the layer and click on this and download it as a GeoTIFF or as an image. But it is important to understand that the query has been resolved by first looking for elevation. So this is the original data that was taken, and then computing a normalization on the elevation data. So this is the first example that I wanted to show you. One important message here is to understand that this data is not in my machine. These data are served online. So when I query in the search bar, I'm actually accessing to a web of knowledge, of scientific knowledge, and that we call a semantic web, because this knowledge has been identified and formalized in terms of semantics and ontologies. So I was searching for elevation with the small cap, but if I, for example, I can reset the context and go to a particular region, like Île at Vilain, which is the region of Rennes. So you see, now I have the context in front of me, and then I can type elevation again. And this is completely different. So what I've been doing is to search for a context, a spatial context, by starting with an uppercase and then clicking enter. And then with the lowercase, I searched for elevation, and now I have elevation in the area of interest. So a couple of things that I didn't mention is that in this icon, I have the spatial resolution, and in this icon, I have the temporal resolution. I can change both of them at the beginning of my analysis here. So I can set precisely at which resolution I want to work. For example, well, the system, when you are in the default situation, is giving a default spatial resolution, and I can change it to, for example, 150 meters. The same goes for the temporal information. So the default is the present time. I can definitely go and change, for example, 2018. And if I want to have multiple years, I can change them at this stage. Yes. So this is how to set the context. So all the queries that I'm doing are completely conceptual. I'm not looking for a specific data or model, but I'm looking for a concept here in the search bar. And this concept is resolved by the machine through machine reasoning. And the machine is able to match data and models, to combine and assemble them in a way that matches the context of analysis. And the context of analysis is precisely this. Can be let's say, the spatial context and the temporal context, but also their scale. So the resolution, the temporal and spatial resolution. One more example that I wanted to show you is there are operators in the system, like this one, type of. So I can just click enter here. And now, for example, I can click geoformation. So if I search for type of geoformation, the system again is taking elevation, but this time is giving me another model, a little bit more complex than normalizing everything. This is actually classifying all the landscape in terms of type of geoformation. So flat type, peak type, slope type, and valley type. So what is different from before? This is the data flow. Well, again, I take the the basic information is elevation. This is classified in terms of terrain morphology, and then giving me the final output: flat peak, ridge, shoulder. Now, this algorithm has been taken by scientific publications and implemented by us, but we didn't invent anything here. Next example is that so far, so I can reset the context again. Let me go again in our context here. So far, I've been showing what we call quality split, basically spatial variables. I can actually search for concept. Like, for example, I can search for city. And in this particular case, there is only one big city, which is Rennes, and is here. Now, I can also search for towns. Sorry, everything has to be singular when you type in the search bar. And as you see, the towns are many more. So the city is only Rennes, but the towns are all around. And another thing that I wanted to show is that you can do operation on these objects that have been identified. So for example, you can type distance. The system suggests the operation distance to. I can search for town, distance to town. So the town have been identified already. So the distance to town is quite easy to compute for the system. So this is the Euclidean distance from every point to every possible town in the context of analysis. Remember, the towns were here. And this is computed on the fly while I'm basically in response to my queries in the search bar. Now, I wanted to show you how the system is very smart. I was mentioning about the context dependency. So I reset the context. I put the minimum up because it's the lighter one. And I can go around everywhere in the world. So all the queries that I've been showing until now, you can do this everywhere in the world. You can zoom in, zoom out. You can search for places here. Remember, start typing with uppercase. But for example, let's go to Gibraltar. So to show you how multi-purpose can be this system, I can, for example, I can search for restaurants in Gibraltar. Sorry, lowercase. And I get the restaurants in Gibraltar. But this is not actually what I wanted to show you. What I wanted to show you is that the system is intelligent and knows that the context defines the answer in the way that is assembling data and models. So for example, I can search for land cover type here. And this is land cover type. I just click. Now this is taking a little bit of more time, but remember that I can always go and check in the data flow what the system is doing. And what the system is doing is very smart, because basically I'm in I'm in a very special place here. And so around Gibraltar, you have Morocco on the southern part, and then you have Spain on the northern part. And as you know, the land cover type, there are many land cover types. In this particular case, the system is picking Corinne for the European side, and then CCI for the Moroccan side, and is combining the two. So I can click in all the points and see what is the land cover. Broadleaf forest, non-irrigated arable land. You see that, for example, here you have high density urban. This is the way that Corinne classifies artificial surface. But in CCI, you only have artificial surface. So this example is meant to pass the idea that all the searches that are done in the search bar are completely conceptual, while the data and the models that are matched to respond to those queries are left to the machine to select. It's everything is automated using artificial intelligence, and that part of artificial intelligence that I was mentioning before. So semantics and machine reasoning. And the knowledge that appears in my browser is belonging to the network of knowledge that we have put in place. So far, all the nodes that are serving the data are managed by us, but we are actually making it available to every institutions that want to join this way of doing modeling, integrated modeling, and this philosophy. So far, I think I have shown a little bit of the K-Explorer, and I am following quite well what I wanted to show you. I don't know if there are any questions, please. You can write the questions in YouTube, or you can also. Yeah. So at this point, I think I will pass to artificial intelligence, to ecosystem services, because basically this is what everybody expects to see. So resetting the context here with an X, and I can go anywhere in the world. Let's go back to France, where the school should be. So the technology that has been developed for developing models for ecosystem services so far we have developed some predefined queries. So basically the idea is that the search bar itself is not super intuitive. I mean, you can search many things here, but it's difficult to arrive to a query related to ecosystem services. So we have prepared predefined queries, and that you can access them just by clicking the spacebar. So by clicking the spacebar, you have these multiple predefined queries, and these queries are divided into thematic chapters. For example, carbon storage, pollination, flood regulation, outdoor recreation, sediment retention, and many others. So the models that we have published and are endorsed are those with this this icon. Other models are in development. Other models are very experimental. You can just browse around with this icon and see their meaning. So for this particular example, I wanted to show you the value, let's say the pollination models. So the pollination models are meant to give you an assessment of the importance of pollination, and you can run all these models everywhere in the world. So for example, let's click a little bit here in the center of France. I just type the space bar, and then I click on net value of pollination, and I press enter. Now, this query is a bit more complex than the queries that I've been showing until now. If I click in the data flow, you can see that the way the system is responding to my query, well, it's a bit more structured. So there is the first part, in this part, that basically is using land cover to understand the probability of flowering and the occurrence of pollinators. They're nesting mainly. And then there is one part that is related to the occurrence of pollinators due to weather conditions. So this is more climatic variables. And this part here is more related to the need for pollination from crops. So the system has already computed everything. And I can see that, for example, the final output is the net value of pollination. It's a lot of red here. So I need to explain a little bit what this model is doing. This model is basically giving you a positive number when the supply is more than the demand for pollination, and then a negative number when the supply, when there is a deficit, so the demand for pollination is higher. So apparently this part of France, there is a lot of demand for pollination. I think there is a lot of agriculture all around here, but there are only few parts where this demand is satisfied. So these are the white parts. The green parts are the parts where there are more pollinators than needed. So again, the model is, this particular model on pollination is resolved in this way. And all these components here are used to assemble the final answer. So for example, this set of global models that we have produced are able to give you a response in everywhere in the globe using global data that we have made available. So basically the user doesn't have to do anything apart from using the right way to query the system. And some of these global information layers are particularly coarse. Like for example, this one is about the demand for pollination from agriculture. So this is using a 10 by 10 information layer. It's very, very coarse. We are using the land cover to filter the agricultural vegetation. But I mean, the default information that is used here, so the global one, is quite coarse.
There is a question related to this data set available globally.
Yes.
Some people are, Selina is wondering if these are applicable on area with scarce data, some like in remote area and so on, but I think you already answered to that. And Benjamin is also wondering if there are some kind of standard deviation of variance values that could be derived from your different ecosystem services index.
So the first answer is for Selina, that we are providing global information layer to resolve all these main queries. So the ones that you can access to by pressing the space bar. All of these models are basically, they have a default answer using global information layers that we have made available. But a user, an advanced user, and then I will show you in the second part of the tutorial, can substitute any of the informational artifacts that are basically explained here. So any part of this model, any part of these components, any of these bricks, can be changed with the local information. And then I will show you later how to basically annotate semantically your local data. So this is the first answer. The second answer, I think, the question is related to, so far these models that I've been showing are deterministic models. So they have a number in every pixel. And for example, in this particular output, you have a number in every pixel and one number that goes from -1 to 1. So this is a deterministic model giving you one number as an output. There are other models like the one that I will show you later, like Bayesian networks, that allows you to give multiple outputs. So for example, the output of the Bayesian network is a probability distribution. And in that case, you can produce map with the mean values, but also with the standard deviation. So yes, both are available. Okay, so this is for pollination. I can try other models like, for example, vegetation carbon. This is implementing the IPCC official methodology.
Maybe you can complete your description and with one example of where you get these models, where you get this information from the IPCC or any other publication.
Yes, I will show you
later. Okay.
I'm coming to that. So this is the data flow for the carbon model, and the carbon model is giving you the vegetation carbon mass in every point. So I can click, and this is given in tons per hectare per year. So, good question. How do we implement all these models? Well, I will show you later in the modeler how we implement the models, but the model themselves, so this is a new part, a new feature that I didn't show until now. For this particular predefined queries, every time you run them and the model is completed, they are producing also a report in a narrative format that is also produced on the fly after running the models. And this is using, well, I mean, this documentation was human-made, but is assembled when the model is computed, and is also including maps and references and everything. So for the, just to answer to these questions, but for both models, so the pollination model is largely based on this publication from the JRC, it's Estimab. While the IPCC methodology for carbon is largely based on this publication, the new IPCC Tier 1 Global Biomass Carbon Map for year 2000. And one thing that you might have noticed is that the report basically is assembled and changes on the fly while I add more queries. So now, for example, I'm showing you the report. There are the sections on pollination and carbon. But let's try, for example, to run also the recreation one. This model takes a little bit of more time, but let's see. I mean, I'm using a quite coarse resolution, as you see, so the models are going quite fast. So the data flow now becomes huge because we have the pollination part here the vegetation part here, and this is the recreation part. So the recreation part is what is looking at many things of, let's say, attractiveness features from the environment, from the landscape, and also on the presence of users, recreational users, mainly the population in the cities. So you can see I can zoom in, zoom out. I can basically interrogate this data flow. And I can click on each of these boxes so that I know exactly how the information is produced. Like, for example, the solar radiation for the pollination part is coming from this layer. And this layer is originated by WorldClim and is giving the solar radiation, the average between 1970 and 2000. And if I want, I can also go to the website and check that. So it's completely documented both in the data flow and in the report. So the report is a bit different because it's using a narrative format and is more like a paper, let's say a scientific article, or with the classical sections on well, introduction, methodology, maps, annexes. So system is, for example, at this stage, I know what is the supply side of the recreation model. This is a model, again, it's an indicator from 0 to 1 saying how attractive is the landscape from a recreational perspective. And mind that I'm talking about recreation here and not tourism, because this model is meant to capture daily trips, daily-based recreation rather than touristic flows. And when the system, when this model will be completely observed, okay, so this is the supply part, but this is also taking into account the presence of recreational users. So as you see, the area around Rennes becomes more important, and also the area around, I don't know which city is this one, Le Mans. Why? Because basically the closer is a recreational site to the population, and the more likelihood is that the recreational users will go to this site. And the report now includes, as you see, has changed, and there is also the documentation about the recreation model. Also, the recreation model is largely based on the work of JRC estimate. So what is the take-home message of all of this? That we have this palette of predefined queries. These predefined queries are, let's say, more complicated models, but the technology and the philosophy is basically the same that what I was showing at the beginning. So very simple, semantic, concept-driven searches here that are connected to a web of knowledge and artificial intelligence that allows to responding to these queries using semantics and assembling the right informational artifacts for the right queries. This palette of ecosystem services related queries is available for every user. So anybody that registers as a user can go anywhere in the world without providing any data, will be able to perform these queries. and get a default, let's say, an answer using the default global data available. In a more advanced way of using the system, I will show you later, you can include your own data, tag it semantically, so the system knows that also the local data becomes part of the knowledge base. And then the system is smart and will be able to pick your own data while resolving the same kind of queries. I don't know if there are more questions at this point. I think
not yet.
Okay, perfect. Thank you, Thomas, for giving me some feedback here. I feel very alone with my voice. Okay, so I think I showed you the Explorer generic use. I show you the ecosystem services palette with the predefined queries. Now I want to basically stress the fact that this technology is completely generic, so it's not meant to resolve only ecosystem services related problems. Okay, we have, let's say, the generic way of using the search bar, which is this one. You can type stuff in the search bar and hopefully you get an answer. You can press the space bar and get the predefined queries. Now we are working on delivering more, let's say, thematically customized user interfaces. And in particular, we have been working in the last months with the United Nations Statistical Office for an application dedicated to natural capital accounting. So what I'm showing now is not completely available to everybody. You can make a request in the profile management part of the website. But because I am a special user, I didn't show you this part. So if you go to the bottom right, you have all the information related to your user. Please forget about my email. And so you see that basically there are these icons. These icons are the same ones that you should see in the control center here when you start the system from the control center. And because I'm a special user and I'm in the natural capital accounting group, so I have this app available, so I can click on it and see what happens. Okay. So on the top of the generic user interface that we call K.Explorer, we can develop any kind of application that guides the user to produce more maps, or more outputs of any kind, and not only maps. But for example, in the particular case of natural capital accounting, the main outputs are not maps, but tables. So natural capital accounting is about the change in the natural capital from one time step to another time step. And basically, we are trying to use the same, to match the same kind of usability with an application like this. So let me reset the system. And for example, this is how to reset the context. And in the region of interest here, you see you have where and when. So right now I'm using the map boundaries. So the context is set according to where I am in the map. But if I do this administrative region, so this administrative region, then the map becomes alive and starts suggesting me possible administrative cases, administrative regions for the analysis. And as I zoom in and zoom out, these are changing. Now, this is, for example, the same that I was using before, let belong. So let's say I want to see the ecosystem extent account for this particular region. So I will explain about all this section later, but very quickly. Administrative region, this is the spatial resolution, this is the beginning, and this is the end. So my analysis will start in 2010 and end in 2019. So let's do the ecosystem account analysis. I click on these three dots, and I have different options. Ecosystem change summary, this is the simplest table. I just click on it, and then the system starts calculating. So natural capital accounting, as I was saying, is about the change in natural capital. And you have this kind of changes. You have, let's say, you have thematic chapters in natural capital accounting. The first one, ecosystem accounts, is how much of a certain ecosystem is available in a certain moment of time and how much is changing over time. So this is what we are doing now. Condition is about how healthy is the ecosystem that we are analyzing. So, for example, for this particular app, we are doing, we have provided some solution for forest conditions. I'm not going to show them now. Then you can basically assess how the ecosystem services quantified in biophysical terms are changing over time, and also their monetary value change over time. So I decided to show you only the ecosystem extent part. So this model is, first of all, is establishing the ecosystem types. And this is using the IUCN methodology. I will show you later in the documentation part. It's quite coarse in the region. You don't have many ecosystems, but well, the majority one, the major one is cropland. Then you have urban ecosystem. Then you have temperate forest. Then probably something related to water. Yes. So ecosystem, the ecosystem is classified. Ecosystem type is classified, but is classified over time using these variables. So the land cover type, the mean annual temperature, the elevation aridity index, if the system is mountainous or not, and the temperature, and is quantified in terms of extents. So exactly what I was saying, every ecosystem type is measured in terms of area, square kilometers, in 2010 and in 2090. And the change is, the net change is computed in this table. So all of this was done automatically just by selecting a context of analysis, the time, the temporal and the spatial resolution, and then basically clicking ecosystem change summary. And this produces, instead of the tables that we have seen before, we also produces the table, the maps that we have seen before, but also produces a table that can be exported in an Excel spreadsheet. I need to take a sip of water. Sorry, Excel causing problems. So this is the table exported in Excel with all the ecosystem types that have been identified, their spatial extent, and they change between the two years of analysis. I can close this. Now let me show you the report. There is a little bit of introduction about the SIA framework, which is the System of Environmental Economic Accounting. This is the standardized way approved by the UN on how to do natural capital accounting. Then there is one part explaining ecosystem extents. In this particular methodology, we are identifying ecosystems based on land cover, aridity, mean annual temperature, type of landform, elevation, and this is the output, the ecosystem type. So this methodology is not invented by us, but is taken from the IUCN global ecosystem typology. And indeed, if you have seen the table itself, it's also saying that this typology is based on the level 3 of the IUCN global ecosystem typology. So I am producing not only maps over time, because obviously, as I said, I mean, the system is knows the context, and the context is the windows through which you are looking at the world. The scale is important, and temporal part is important, and also the spatial part is important. So I have the spatial resolution here, and the temporal resolution here and here. The same, I can do exactly the same for land cover, for example. This is should be a bit fast because the land cover has been analyzed, but land cover, as you see, is giving you a little bit of information there on land cover. So basically, the system will compute the same ecosystem change, but for land cover. Okay, I think I did something wrong at this point. But this is the idea that I wanted to pass on, is that we have a generic user interface, and then we can provide applications, thematic applications on the top of it that are devoted to resolve particular specific queries, like, for example, in this case, those related to natural capital accounting. So I covered the part on the palette, the SIA application. So now I would like to start with the modeler, which is a little bit more advanced. Please let me know if there are questions on this part. I can stop here. I'm actually exiting now the online engine, because what I'm going to present from now on requires the software download. So remember that we were here. I had started the engine, and if I click on this, basically I can access the same K-Explorer user interface. Again, just to repeat a little bit, I can start typing with uppercase. The system will suggest possible administrative regions. In this case, should go to Sardinia. Okay, now I have it, and then I can do all the type of queries from elevation. I mean, I'm just showing elevation because it's very intuitive, but I could show you many of these variables. We have basically 200 global layers about any kind of variable. Okay, so Explorer from by clicking the globe icon in the bottom left part from the control center. Engine is on. Now I'm starting the modeler interface, and I'm going to show you a little bit of how to use the modeler. So the modeler is based on the well-established Eclipse IDE. It will start in a minute. We have a team of developers in BC3. Ferdinando is the lead developer. Then we have Enrico, we have Steven, and Andrea. Many Italians in the team. So this is how the modeler interface looks like. Actually, I'd like to. What I'm going to show you is a set of nitrate-related models that we have developed for the case study in France. But before that, I want to show you basically a little bit of this interface. It's a little bit more complicated than the other ones. Here basically is the interface that the modelers use to create new models or annotate data sources in a semantic way. So on the left side, you have the projects in which you are working. The first thing you would have to do as a new user is to create a new project. For example, I can create like an Alice.winterschool. And it appears here when a new project is created is almost empty. So, for example, I need to create a new namespace to start adding my own code. Now, for example, I want to show you how to import your local data. So I'll just call it data. This is winterschool.data. Sorry, the other name was already existing. Okay, winterschool.data. You have the namespace here is empty. What you need to do in order, for example, to add your own data, I have prepared some data that are related to to river-related information for the Cusnon case study. So you have resources here, and you have some data that you want to use. In this particular case, I want to use these two TIFF files. One is about the temperature in the river reaches, and one is about the stream flow in the river reaches. So what I need to do is just to drag and drop the layer on the resource here. What happens when you do this operation is that the system ingests the information, the layer itself, runs a lot of tests in order to understand what the information looks like. You have this resource editor that appears when you left click on the resource. Basically, the system has identified also where the information is located. I can give them more information in this resource editor. For example, I can set the time of this information. This is for 2018. You can just save. Okay, what happens is that I have this layer in the under resources here, and so far we have introduced non-semantic information in the system. Now, in order for the system to understand that this information is part of the semantic knowledge base, I need to annotate this layer semantically. So the way to do it is to connect this layer with its own URN. I copy the URN, so I right-click on the layer and then copy URN. Then I go here, and then I write model. This is the universal keyword for starting a model in our system. This is the URN itself. And this information is related to temperature. So as now I'm writing, and then I will explain why I'm writing this. UPAC water. I am temperature. So of Earth reach. This is also during summer. So in the 3 warm months. And this is the unit of measurement. Now I end the modeling statement with a semicolon, and I Control S, and then I save the information here. Now, if you go here, you have water temperature. So what I've been doing is basically to connect a resource identified with a URN with an ontology related to that. And this ontology basically says that this is the temperature of the water in the river reach during the summer months. And this temperature is measured in Celsius. So this language that you are seeing here is called KIM, stands for Knowledge Integrated Modeling, and is a declarative language that we have developed in order to do semantic modeling. And as a grammar that is very similar to English and reads like English. This is very readable, as you can see. So model this particular resource as water temperature of reach during summer in Celsius. Now, why is written like this? First of all, everything that has to do with chemistry is related to the UPAC authority. So this basically allows us to not contain all the taxonomies and identities that are present in other dictionaries or tesauros. In this particular case, we are referring to UPAC for everything that is related to chemistry. So that's why we write UPAC and water. Then IM temperature is, let's say that this part here is the namespace that contains the concept. The concept itself is temperature, but I will show you later how to import the knowledge base. And this is the generic namespace that contains the concept of temperature. Reach is the river reach, but is contained in the namespace named Earth, and the same goes for summer. So I will show you this in a minute. Now, it's very likely that when you do an annotation like this, the engine is not completely synchronized with the modeler. So I have prepared this already before. And I was telling you that basically this information is constrained to the case study in France. So I opened the Explorer. The Explorer is like this. I was in Sardinia. I need to reset the context. And I reset the context. Then I go to the French context. This is the French context is declared in the same language using the WKT coordinates. Here I'm also specifying, for example, the spatial resolution and temporal resolution. So this is our case study in France. And the information that I have just annotated is water temperature. I drag and drop it on the system, on the target here. And this is now available in my context of analysis. So the water temperature goes from 16 degrees, 16.01 to 16.6. And I can zoom in, zoom out, click on the points, and see the values. So this example is to show you how to annotate local information semantically. I have done the same, for example, for stream flow here. So the stream flow goes from 0 millimeters to 3 millimeters, more or less. And if I click in the data flow, I can actually see that this raster resource is exactly the TIFF file that I have imported. You can see it here, current flow sum.tiff. And right, this is basically everything you need to know about how to import local knowledge. So you can drag and drop your information layers here, and then you use the URN in the namespace, and you link the URN to a concept using the k.LAB language. Any question? Yes.
Yes, there is a question from Benjamin. Can we share data with others by dragging and dropping our data in the engine?
Yeah, good question. So the way I was exactly going there. So the way to make your own data available to the public, or you can also be, let's say, a reduced set of users is also possible, not entirely public, but available. Is basically, remember that you have a resource, like, for example, this one is Streamflow. You click on it, and then you have the resource editor. And then you have a button here called Publish, and you click on it, and then you have basically a guided way to publish this information. So this is technically possible, and it's already available. The only issue is that so far we are the only one having our nodes in the system. So we will be hosting the data if you publish it this way, which is totally fine. I mean, we are happy to receive data from all the users. But you need to understand that basically what we are trying to build here is a Wikipedia-like model for doing integrated modeling. And so part of our strategy is to include more and more nodes in the network, so that we have institutions completely dedicated to, for example, data management, and because, I mean, there is a lot of work involved in keeping the data in well shape. And we hope to have authorities for data very soon. We are already working with many institutions, ISPRA in Italy, SANDI in South Africa, I mean, these are institutions that they have data in their DNA, and we hope to include them in our partnership. Any other question related to that, or other questions?
Not yet, but Benjamin is answering that it is great, really great.
Thank you, Benjamin. Okay, yeah, I'm going a bit all over the place here with this presentation, but I think it's okay. So now what I want to show you, so I showed you the creation of a local project. I show you how to import your own local data and to tag it semantically. Yes, now I need to show you that basically everything that we are doing, all the projects that we work on, including the source code for the entire system, is hosted in open online repositories. So if you go to bitbucket.org, which is something similar to GitHub, if you're more familiar with GitHub, this is Bitbucket, this is by Atlassian. We are using all the Atlassian suite for this project. So you have the k.LAB project is the source code for all the software stack. And but also there are also all the projects, so the projects written in Kim, which contain the models and the data annotations for everything that we have been working on in the past. So for example, if you click on projects, you have the ARIES folder. Under the ARIES folder, you have all the ARIES related projects. So this is for the French case study, for the Irish case study, for the Portuguese case study, and for the Spanish case study. If you want to import this project in the modeler, the way to do it is to do this procedure: file, import. Then you have two choices: is projects from Git. So I want to import it from Git. This Git project could be in my local repository, and I will do an example later, or in an online repository. In this particular case, this is in an online repository. So I go into clone URI. Now I need to here copy and paste the address of the repository that I want to import. If it's the French, for example, case study, I just go here, I click on clone, I copy, and then I go here and I Control V. And in this way, I start the procedure to import the project. I have already done it here, so I won't go until the end of this procedure. And when I'm done, I'm actually having the entire project in my workspace here. And I can observe all the models that are available in the project. So you see, I mean, we will talk maybe more about this later on, but we have models about pretty much everything in the ARIES project, from fire, ignition, to recreation, to water quality. I want to show you a couple of examples about water quality. Very fast, because I don't have much time. So I reset the context. I observe the context of analysis for the French case study. Just to double check I am here. Okay, perfect. Then I have some examples about nitrates. So this model is about nitrate load. I can just drag and drop it, and I want to show you how the model is written. So this model is modeling the nitrate load. So this is the non-semantic name, nitrate load. This is the way we express it in semantic terms. It is the ratio of nitrate mass on the watershed area. And this model is observing as input the area of the subcatchment, the proportion of broadleaf forest in the area of the subcatchment, and the percentage of surface occupied by broadleaf forest within a 200 buffer in the adjacent hill slopes. This is the riparian broadleaf forest proportion area of watershed. And how do we combine these three outputs? We combine these three outputs using this particular resource. And this is something that I want to show you. First, let's see. The output is here. So we have the nitrate load in kilograms. It goes from 25,000 to 125,000, more or less. The majority of the observation is between 75 and 85 K. And as I said, you can observe, click, see the histogram, click on the points, see the values. Okay, so how was this model developed? So as I said, I'm using this URN. So this URN is actually pointing to a resource that is here in among my resources. So this is called BN-NO3 low. BN-NO3 low. This is the resource. I left click on it, and then I have the resource editor open. So this is telling me that this resource is a classifier. So this is actually a machine learned model. In particular, is a Bayesian classifier, and uses as input the three inputs that I was showing you before, the area of the watershed, and so on. If I want to see this model, this machine learned model, I can actually export it. So I right click on it, I can export the resource. And this is, for example, you can export it in many outputs, but let's say, let's export it as a BIF file. BIF file is basically a network file, Bayesian network file. I can open it with the system that we used to create it. So this is the Bayesian net editor in Weka. I can open and go to Winter School. This is the BIF file. This one. Okay, so I need to lay out a little bit. So the output is a nitrate load. The inputs are the area of watershed, the broadleaf forest proportion, and the riparian broadleaf forest proportion. And you can, I don't know if you know about Bayesian networks, but basically it's a directed acyclic graph with computational, with probability tables attached to them. And I can see the probability table here for this particular node. Now, this is not very easy to navigate the Weka editor. So that's why I want to also open it with a text editor. So file, open file. One sec. Yes, so the idea is that what it is, it's basically a combination of states for each given node and the output node. So the output node is the nitrate load, and the input nodes are these nodes, and then you have all the probabilities that link every class, every interval of this, of every node. So you have, for example, 3 intervals in each node, and all the possible combinations are matched with a possible probability here. This model was developed with data. So what we did was that we used a database, a large database from the institute, Hydraulic Institute in Cantabria. And we used Weka as an engine to do the machine learning part. So all the machine learning components in the system are deferred to the Weka system, which is completely included in the system. And there you have tons of possible classifiers that you can use. We like a lot to use Bayesian network because they are not complete black box. So you can also navigate the structure of the model that is created. I want to show you very quickly how a machine learning model is created. So I had done this before, just to give you an idea. Let me see if I need to reset the context. This is a learning test case that I was running before. This is within the case study of Spain. And this is the model that I'm going to launch now, and it's going to run on the fly while we speak. So I will be learning the land cover type based on 4 predictors: the distance to the coastline, the slope, the elevation, and aspect. I mean, the list of predictors is very limited and is not typically what I would do, but this is done just for explanatory purposes. So learner, just drag and drop it here. So what is important to notice is that instead of the model keyword, which would be, for example, used to show you the land cover data, so the land cover data is annotated in this way. It's modeled, the ULN, as land cover type, and then is classified into, and then you have the different kind of land cover classifications. Now, the system here is actually learning using a Weka BaseNet classifier, is learning the land cover type, which is being provided by our case study partners, ARIES Cantabria, and using all the predictors that I was explaining from. So what we did was to learn land cover type, which is this one. I'm running at a coarse resolution just because I want to make a fast computation. I could do this at 50 meters, at 10 meters if I have time, just taking it a little bit more time. So I'm learning the land cover type based on the distance to coastline. All of this has been computed on the fly. Slope is coming through a WCS service, elevation WCS service, aspect also WCS. All of these, they have been used as predictors to learn land cover, and this is the output. So the output obviously is not going to be amazing, but what you have is in the report, you have exactly how precise was the model in learning the land cover type. And this is the typical statistics for a machine learning model. This is the confusion matrix. So you see that, for example, I think coniferous forests are completely missed, and agricultural vegetation also are missed. But it's just to give you an idea that the system is able to learn a variable using predictor variables. While this, for example, would be the case study in Spain. So I mean, ultimately, we didn't use our modeling routine for land cover change within k.LAB. So this work was done by Thomas' group. But this could be totally feasible in the system or within the system. And this is land cover type at this coarse resolution, 150 meters. Okay, so it's 20 to 5. I think I covered more or less what I wanted to cover. I think it was a bit challenging because this, let's say in general, the software stack, as you see from this slide, is quite distributed, and there are many pieces to explain. I have been able to explain quite well, I think, the Explorer part and its applications. I went a little bit through the modeler, which is the entry point for people that want to contribute data and models. And this part is the part that you don't actually see because it's constituting the semantic web itself. So the engine, you see it because you need it as an entry point to the semantic web. These are the nodes of the net that are serving data. And these are the nodes of the net that are authenticating the users and managing basic data privacy and all that part. Yes, the idea is that basically with ARIES, I just gave a very little example about nitrate load. Well, I could continue a little bit because with that part on nitrate was quite interesting as we work with Thomas to make it as calibrated as possible. So, okay, I'm in the Explorer. I observe the case study, and then I can drop model after model. So the load, for example, can be converted into concentration. So this is the load as before. Observing the three main inputs and then giving you. Yes?
Stefano, there is another question. Do you have example of the time required to run models depending on the resolution and the number of the data layers?
Yes. I mean, if we are talking about the models that we have made available already, it really depends on the context that you are analyzing. I mean, you can go from 20,000 pixels to 50,000 pixels. Actually, with this online engine, you have the power to break our system, because if you zoom out and you make a query for elevation for the entire world, the system will try to give you an answer with probably, I don't know, 50,000 million pixels. And so this, I mean, obviously the engine that we are providing online is a powerful machine that is giving you answer in the fastest way possible. But otherwise, if you're using the software download version, so the control center, the engine runs in your machine, and that is basically using the computational power of your machine. So that depends a lot on the quality of your machine. But I mean, the answer is it can take up to 6 hours to run, for example, a complex model like recreation for an entire continent, which is not bad. I mean,
I think, okay, there is another question, like a practical example from Marie, but maybe you can just finish your example for the Quenon River on the nitrates issue. And then she's asking if it is possible to show an example about how to copy and paste an existing model and to use our own land use or land cover map data.
Yes, sure.
because I think that people are quite interesting to maybe replicate or apply the existing model of k.LAB, but adapt that to their case study with their own data set.
Yes. So first of all, let me finish the models on nitrate. So this is the calibrated nitrate concentration, and this is, after that, I will show you the level of. Actually, Thomas, you can explain the output of this much better than me.
Yeah, I will support you, don't worry.
Okay, so this is the initial model that we ran before. I was showing you that, and this is basically a Bayesian network model. Now we convert the nitrate load into nitrate concentration here, using this particular algorithm. So this is the way to define an algorithm with two inputs, stream flow and the load. Now, because that load was not taking into account the agricultural area, which is quite important, we have made a modified version of it. We call it calibrated nitrate concentration. And this is taking into account basically the fertilizer coming from the maize crop fields. And because in France you have this regulation that tells you basically the traffic light, it's under 25. Under 25 is low, between 25 and 50 is moderate, and above 50 is high. We made a model that basically is taking the output of this and assigning a red and orange and yellow, sorry, and a green color to these three classes. And I think it was already done, but it was here. Okay. So this is the level itself. As I was telling you before, I mean, this map in the background, you can change it from all of them. You can also decide to not have it in the background. And in this particular case, to see the traffic light colors, for me, is much better to not have it. So in the red parts, you have these areas that are above the critical threshold. Then you have the yellow areas in a so-so situation, and then the green area that is green light. Thomas, do you want to say something about this?
Or maybe just to complete that, basically we use a model of nitrate concentration that has been developed from the Cantabria team, that has been applied and tested over the Spanish region. And one of the main predictors was the proportion of forest, because they have very low concentration of nitrates in the flow. Of course, it was not representative of intensive agricultural area. So we adapt this model by using the proportion of crops within this. Okay, sorry, I will start my video. Okay, so we adapt this model by just replacing the proportion of forest by the proportion of cropland within the area that is contributing to each part of the stream here, and we compare this result with current observation of nitrate loads and nitrate concentration, and I would say that it is pretty good, but it means that obviously it does not take into account all the farmer practices that could be particular from one place to another. But basically, I think we exactly recognize which stream are in the worst case situation and which one are in the best situation. So we are pretty happy with these results.
Great. Okay, then I need to answer to the question about land cover, how to annotate it. And I have an example here, for example, in Alice's test. So this is the land cover TIFF information coming from Cantabria. I just import the TIFF file, as I was showing you, from my folder to the resources. I just drag and drop it. And then the way to annotate it is this one. So model, and then the URN, calling the non-semantic resource. This is basically the TIFF file. Now I need to tell the system that this information is land cover type, and this is how you do it, as land cover type. But because land cover type is not a numerical variable, is a classification, then I need to match all the codes that are in the TIFF file with a concept, and the concept are the land cover classes. So in the particular case of the Spanish case study, but also I think we use the same land cover classes in all the case studies of the ARIES project. So it's broadleaf, coniferous, shrubland, grassland, agricultural vegetation, bare area, artificial surface, and water body. With this simple way, when I'm in a context that is Spain, sorry, let me go to that with the minimal. So I can go, for example, I can go to the Spanish case study and check for, so this is partly the land cover, the Spanish case study, and partly not. I type land cover type here. And now we will see that the system will obviously try to resolve my query with the best available information. And as you see, it was partly taken with the Corinne land cover that is available at the global, at the European level, and partly using the data that I have fed to the system. So you will see something very strange here, where basically you have Corinne outside the case study, and then let's say the ALICE land cover classification inside the case study. This is just a way to show you that the system is smart and can resolve queries according to the knowledge available in the system. I hope this was clear enough as an answer. And once you have made available your land cover information to the system, then because it's local specific, it will likely have priority on all the other information. So it will feed all the models based on land cover. And mainly the ecosystem services models that I've been showing at the beginning, they are largely based on land cover classification. So you can affect the models there, for example. I think I'm finished, and I'm very happy to take more questions. Or if you want, Thomas, we can discuss a little bit the generic implications for the ALICE project that we wanted to make clear to the audience.
There is one technical question before maybe to do so. Benjamin, still the same. He's very interested. He's asking that, as in R, can we launch k.LAB several times simultaneously on the same computer to test several simulations at the same time to save time?
Yeah, I mean, the computations run in parallel. So you can, when you're using, let's say, the engine from your own machine, you can run multiple models at the same time. You don't have to wait for results in order to launch the next one. So you can save time there. Then if you have really big, let's say, queries and analysis, and you need to do a routine kind of analysis on, in a repetitive way, then you need to, I mean, there are ways to write a script that does this for you, like you do it in R, basically. but this is a quite advanced way of using the system. And if you want to do that, I mean, please contact us at support, and then we will try to support you.
And Mary, that was asking the previous question, she's really happy about your answer, and she thinks that k.LAB is awesome.
Okay. I mean, the philosophy of k.LAB is, as I was telling you, it was born for ecosystem services, but we realized through time that this can be applied to a whole bunch of modeling problems. And it's the philosophy behind is basically to make what Wikipedia has done for encyclopedias. We want to do it for modeling in general, to join the information, to integrate the information that is out there, and to involve partners that are willing to cooperate, and to make it as open and as accessible as possible, so that the world can make smarter decisions, sustainable decisions with better information.
Okay, and so I have maybe one or two questions more related to maybe the perspective of k.LAB. We have seen this morning that most of the land cover or the inputs that you are using come from derived satellite-based imageries. And because satellite images are also data that are provided by any kind of data provider that could be requested with WCS services. Do you think that there could be this kind of maybe land cover automated classification based on, I would say, live stream satellite images from Sentinel-2 or Sentinel-1 as well?
Yes, it's totally feasible. On the technical level, there is no doubt about how to do it anymore. So we know that it's feasible and we know how to do it. The only issue is to have all the relevant partners in the same room and willing to cooperate. But we are talking with the European Spatial Agency. We are talking with NASA as well. And we hope to have this on the fly, let's say, queries to the satellites available soon. We have a demo already about that, but nothing that we can actually offer to the users at the moment.
And in ARIES, finally, we did not integrate everything into k.LAB because we were not into that at the very beginning. But I think that now the attendees can consider that it is completely feasible to integrate all this habitat mapping, maybe connectivity mapping, and of course ecosystem services, maybe in few months or few years, if they do collaborate to k.LAB. But well, I think that it is also obvious that we need scientists like Jose this morning in order to better translate all these requirements in terms of in situ field work, in order to better define what are the land cover types, suitability maps, all these prediction models and so on. But I think it is a great way to have more generosity and replicability in all these scientific projects as well. I don't know if you have other questions, all of you. Maybe also I can ask to Jose and Hugues to be part of this discussion now, because it is, I think, quite open. I don't know if they are still there. Yes, they are.
Yeah. Hello.
But I think it is good to have a broader overview with what are your feelings, maybe what are your reflections based on this presentation today.
Yeah, thank you. Yes, I think the storytelling has been, from my point of view, successful to show that, to demonstrate that we can manage our own data, to be each time more and more objective in the conclusions that we get. And this presentation that Stefano made is like the final step of integration information. But I think that, or no, I think is that was we have been done in ARIES. We use the in situ information, satellites, and multidisciplinary teams for understanding reality, for understanding how landscape change, evolve, function, and so on. And finally, once the information has been worked, has been clear, discussed among experts and scientists, these kind of approaches allow us to integrate everything, to communicate the information from the river ecology with landscape dynamics, with vegetation patterns, to put everything in common for running with the same algorithms, information for different case studies, for different time periods, and finally getting information from ecosystem services and different applications. So, well, I think we try to demonstrate how to integrate information with different platforms, and these final capabilities of ARIES and k.LAB world integrated modeling community that Stefano showed is like something important to have in mind to any scientist and data manager to know that there is a technology over there that can integrate everything that we think correctly into a common world that will allow us giving integrated conclusions.
Yeah, I mean, the ARIES project was ambitious in many ways. If I could show you the list of models that are implemented, it's humongous, and there are still many that we are missing. I mean, we weren't able to completely integrate the hydrological parts. So, for example, that's why you have stream flow coming as an input. So it's loosely coupled from an hydrological model. Same goes for a water temperature model. So these two parts are the parts that we are still missing and require a little bit of additional work in order to integrate the full computational chain in k.LAB. But I think nevertheless we were able to present the case for basically showing the added value of this methodology of integration in general for solving real world problems, which is the main issue with an Interreg project, because we need to remember that the Interreg projects are not for pure research. They are for being applied in the domain of cooperation and solving real world problems.
Yeah, but there is no solution if there is no research behind. So, and ARIES, all of us know that we have been discussing quite a lot of people from the different institutions to have some clear conclusions that were included afterwards in the k.LAB platform for modeling ecosystem services related to that patterns, that functions, and so on. So we have to know what are we talking about, research, for then apply into sustainable solutions.
Yeah, and I think the world needs science today more than any time in history. And having good science in the background of any decision taken, I think, is a good starting point.
Right. Okay. Just trying to. I don't know if there are any other questions. I'm just trying to move my window. Okay, it's getting better. Well, I think at least two people are quite really interested by what have been shown today and this afternoon. In terms of short statistic, we start with 90 people, but we lose approximately half of people during the day, and it's getting late now. But it's not a bad score, I would say, because at the very beginning, when we talked about organizing this winter school, we were hoping something like 20 to 30 people, and finally the COVID has allowed us to be with almost 60 to 70 people this afternoon. So would like to thank you, all of you, to be part of it. And just maybe to finish with few slides in order to conclude this winter school. Okay, I start this slide about this first very simple illustration about what is the landscape. And of course, it is something that is very complex, with a lot of interaction between humans and natural processes. And we try to define and to show some methods in order to characterize this landscape as habitats, as functions in terms of connectivity and in terms of ecosystem services. I think that the example provided by Jose, Hugues, and Stefano were quite enlightening what could be done, but of course we were not exhaustive. And I would like to just open the discussion, or maybe open your mind about the fact that landscape are, of course, dynamics. This has been mentioned several times during the day, but of course there are several processes that could make the landscape evolving fast or not. But there are, of course, anthropogenic disturbances like pastoral fires. There are some kind of legacies in terms of past practices. There are natural processes like encroachment or grazing, meaning that I think we should more take into account this kind of landscape dynamics into our assessment. It means that if we want to have maybe more impact towards decision makers and policies, we should better anticipate these changes into the future in order to define sustainable strategies. It would mean that we are able now with this kind of tool to maybe better estimate what would be the trade-off between the gain, the trade-off, the gains, the losses between ecosystem services, habitats, and functionalities by exploring the future. So this is just a way of maybe make a small reminder about what was the philosophy of ARIES. Basically, it was to develop this kind of tools, but also to explore the future based on what if there is no B genes and what if there are B genes, and what do we gain in terms of ecosystem services, or what we're going to lose in the future based on this kind of very simple scenario comparison between business as usual scenario or a B gene scenario. The idea is just to explore the future based on different type of scenario and to apply all these tools in order to make more profitable trade-off analysis between biodiversity, economy, or any kind of environmental assessment. And if you are interested in exploring this part of the landscape dynamics, I would invite you to be part of another seminary, another day of conferences tomorrow. And we have invited Peter Verberg, which is quite a very famous scientist in all the land change science community. And he will talk about the landscape changes and the land use modeling at the global scale. And its implication in terms of ecosystem services. I will make a kind of short review on what could be done at very fine scale in terms of land use and land cover change modeling as well. And Gaëtan Palka will present you one of the model of the land use and land cover change simulation we have developed within ARIES, in order to present you what could be done at a very fine scale that is completely compatible with everything that has been shown today in terms of environmental assessment. So you have the link of the web page where you can find the Zoom link to access this seminary tomorrow morning. And for those that are interested in participating to a more participatory science workshop, there is a workshop in French in the afternoon that will be dedicated to present all this scenario and all this environmental assessment. But of course, it will be in French, unfortunately for all you guys. So I'd just like maybe to thank you all to participate to this journey. And if Jose, Hugues, or Stefano, you have final words, I will be happy to give you the floor. And I just wish you a good day to all of you.
Yes, maybe I can begin. So thank you, Thomas. Thank you all for inviting me. And I think the main there are two issues for the future for us. because landscape are again, going worse and worse because of human forces, because of climate, because of many things. And we will see that the more we are integrated the things and scenes in such models, the more complex the whole model is. So I think the first issue is to be, yes, complex but simple at the end when we propose tools to be available for a planner, for researcher, and so on. So it's the first. I think it's the first main issue we have to focus. And the second one is to continue to develop new concepts and to not be afraid to test new things and to be able to incorporate it on such models. So it will be more and more complex, of course, but I think we are going on the good way, but it will be a bit difficult, and it will be very soon if we want to make something change for real.
Yeah, me only adding just some words about what we tried presenting this morning. With a lot of information, speaking very quickly, I cannot go more slowly, sorry. But what we wanted to translate is that we want to put everything on the table to disentangle the complex patterns, processes, drivers of reality, dealing with complex landscapes, not only using the really available information, but going in detail into multispectral time series of satellite imagery, hyperspectral LiDAR, and everything that can be handled, the drones as Thomas uses, and everything to disentangle reality and to have the capability of defining more simpler indicators or more simple indicators that that we can develop just making complex analysis for trying to put afterwards in this kind of integrated modeling approaches, as Stefano explained us, by avoiding using the complexity of data and methods, by creating something more simple that can be understood, that put into modeling frameworks that interconnect the different parts of reality. That was our idea, and that's what ARIES tried to put in the table for all of you. And thank you very much. It was a pleasure to be here, and see you in the next. That will be more, I hope.
So thank you very much, Thomas, for organizing this. And it was a pleasure, obviously, to be in the ARIES project. For me, an occasion to work with very good people in their own fields, land cover change, modeling, and remote sensing. I mean, you are very, very good in what you do. And for us, very stimulating, to integrate all the possible modeling approaches. And there is a lot of work for us to do to involve the broader community and to deliver the technology in an easy way. I mean, it's challenging even to communicate it to the broader public. And so an occasion like this is always a good test for me to test how the situation is out there, the modeling community and the non-modeling community.
Thank you, Stefano. Thank you, you guys. Well, I think that you said everything. I think it is important to share what has been done, and this winter school has been a great occasion to do so. I hope you will be inspired by what we have shown. Your comments seems to be in accordance with the statement. So now it's up to you guys. And finally, I would like just to thank you also, Mariana, for the technical support that she's behind that, everything, and all the colleagues that participated to this winter school. And I hope you will be able to meet each other soon as well, beyond the COVID situation. So Take care of you and see you soon. Bye-bye.
Bye. Thank you.
Bye-bye. Thank you. See you.
Bye. Thank you.